So we talked about non-permissible values already, so it's not like these are going to be crazy. We literally discussed this 2 days ago. Kind of the same thing. There's just the only ones we discussed were kind of like cos, sine, tan, cotan, right? Where they equal 0. There's options like, for example, when we get down here, 1 plus sine or cos x minus 1. But it doesn't make it harder. That actually makes it easier when those are there. So don't freak out. Promise you. They're actually easier when they're there. Okay? So let's look at the first one. It says, determine the non-permissible values of x in radians for each expression. State the general form for the restrictions below. So we have sine x on the top. Does that create any denominators? No, it's a sine. If we had tan x on the top, we'd have a denominators, right? Remember I told you tan x's create denominators, cotans, secants, cosecants, correct? But sine's good. This is like happy. Yay, nothing there. I do have a cos x denominator, so I have to state all the spots where cos x can't equal 0. Because where it does equal 0, we got problems. Right? Because it would make the denominator 0, and we got issues. All right? So where is cos, which is x, equal to 0? Where is cos, which is x, equal to 0? Yeah. 90 and 270 and every other 80, 180, backwards, forwards, etc. Right? So our first one, we can do this in degrees first, and then we can put it into radians after, if that's helpful. Our first one, though, our first principal angle would happen at where? 90 degrees plus how much? 180s. We'd add 180s or subtract 180s, and we keep landing on those spots. Boom, 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 boom. Right? So we can go plus 180 degrees n, but n has to be an element of the integers, so we add 180s, and it also makes us subtract them indirectly because multiplying by -1 would make it be -180, right? Okay, that's in degrees. It asks us for radians, so we can't stop there. So it's going to be pi over 2, and what's 180 in radians? What's 180? Pi n NEI. We look at B. B is cos x on the numerator. Does cos x cause us denominators? Does cos x cause us a denominator? Ooh, I can't speak. Nope, that one's good. Yay! Then we have tan in our denominator. Well, tan is actually the same as sine x over cos x. So actually, everywhere where sine is equal to 0 and everywhere where cos is equal to 0 are problems. Every 90 degrees. Because where is sine x equal to 0?
0, 90, 270, 360.
0 and 180. And cos is, 90 and 270. So tan actually hits every single one of them. And why does tan? We drew tan. Remember? We drew tan. Tan had asymptotes at every one of these because it would be your x's are 0 there, right? So it would be 1 over 0 or -1 over 0. So these are asymptotes. So those are out. Can't have an asymptote. And then tan equals 0 here, which would make it out because you can't have it equal to 0 because it's in the denominator. So it makes sense that it hits every single arm. So when we go to do that, we said, oh, we could start at 0, and then we add, technically, little 90s each time, right? Plus 90 degrees and NEI. But I told you, when it's 0, you can write that and you're not wrong. You just won't see it as a multiple choice. They won't go 0 plus, correct? So they would go 90 degrees and NEI. But we need it in radians, so it would actually be pi over 2 n NEI. And you box it to make them know for sure that you know that that's radians. If you don't box anything, they're going, oh, this kid doesn't even know if it's degrees or radians. They gave me every answer and they're hoping I picked the right one, right? So we don't want that. They will take off marks. You have to box the radians. If you're going to state both, you have to make sure you box it and you say, hey, here's my radians. This is what the answer is. C gets vicious. Yeah, sorry.
You always put in radians unless it's degrees.
This one just said radians at the top. That's the only reason why I'm doing it. Yeah, so they have to specify. If they don't, they'd have to accept it. So this one here, cotan. Cotan is problem. Why is cotan a problem? because it has a denominator, because cotan is actually what? Cos x over sine x divided by 1 plus sine x. So anything over here is in the denominator, correct? That's in the actual denominator. And then this is a denominator too, right? Do you remember rationals from grade 11 where you did like a over b divided by c over d? Remember that? And then you could flip this half, so both of these were actually non-permissible values because they would flip. So d is currently in the denominator, but when I multiply, c is going to be in the denominator. And then this is in the denominator. So only for rationals with division did you actually state for b, c, and d. When it was multiplication, you did denominators. When it was addition, subtraction, you did denominators. When it was solving, you did denominators. But when it was division, you stated for b, d, and c. You see that? Same thing here. If you write them out sideways, this would be b, this would be c, this would be d. I'd have to state non-permissible values for any of those, correct? So whenever I have a fraction and I go to stack it, I stop myself immediately and write it out sideways. And then it's easier, because remember from grade 11, you're taught this. So you're taught rationals in grade 11 to lead you into these things too. Like they help you with the same rules. It's just fraction rules. So I have to go and say sine x can't equal 0. And I also have to state all the spots where 1 plus sine x can't equal 0. This one, however, I'm going to subtract the 1 over because it's not helpful to me looking like this. So I have to state where sine x actually equals -1 because that's where I kick out all the x's, correct? I just have extra steps. And I can state their non-permissible values separately. Okay? So where does sine x equal 0? Where y equals 0. Where does y equal 0? On the x-axis, correct? So it would just be pi n nei, technically, right? Because it'd be 0 plus pi plus pi plus pi. So this one would be x can't equal pi n nei. So I've done one of them. Then I have to state all the places where sine x equals -1 and say it can't equal those. Well, where is sine x equal to -1? Where y is equal to -1, which is here. And then it would just have to go 360 around, right? So it'd be 270 degrees plus 360 n nei, correct? That would be in degrees. What is that in radians? 3 pi over 2 plus, now I have to go around and around and around, plus 2 pi n nei. So you actually have 2 of them, right? D you're going to try on your own. See how you do. So the first thing I always do is turn to sines and coses where possible. So I'm going to get sine x over cos x for my tan, which is a fraction. So I'm going to put them side by side. Over cos x minus 1, technically over 1. So I'm going to state non-permissible values for this, and that. Correct? So I have to state them where cos x can't equal 0. Cos is x, so that's here and here. So that's going to be x can't equal my first one, which is pi over 2, so it's 90, plus 180, so pi n nei. How'd you do on that one? Good? Okay. Then the other one I have to have where cos x minus 1 can't equal 0, so I have to move the 1 over. So it's where cos x can't equal 1. Well, that's where x equals 1, which is here. That would technically be at 0 plus 360, right? And on and on and on. But in radians, that'd be 0 plus 2 pi n, on and on and on. Do I have to write the 0? No. So I can just go x cannot equal pi n 2 pi. 2 pi n and e pi. Now, sometimes you go to state non-permissible values, and they're actually covered in the previous one, right? So So like, let's say it was cos x equaled 0. And then we'd have sine x equals 1. Well, they would land on the same spots. So then you wouldn't have to state it twice. But you could. There's no harm in it. Okay? So here we have determine the restrictions on tan x plus cosecant x, but now the restrictions are actually restricted. The restricted restrictions. They're restricted between 0 and 2 pi. And why would we have to worry about that? Because when we go to solve, if it's between 0 and 2 pi and we state the restrictions, we really only would have to check for the ones within the restricted domain that you're having to find. So here we have tan, which I would rewrite as sine x over cos x plus cosecant, which is 1 over sine x. So what are my non-permissible values going to be based on? What can't equal 0? Cos and sine, yeah. So basically, cos, whenever you get both cos and sine, you should throw a party. Because those are easy. You don't even have to use brain matter. Where is it found? When it's both of them. Every 90. Every single one of these, right? The catch is, if they want a general, you just go pi over 2n NEI, correct? But it's not general. They want the answers from 0 to 2 pi. But what's on the 2 pi? It's a round bracket. And what does a round bracket mean? Not equal to. So you cannot give that answer, correct? So I can give 0 because it's equal to it, correct? I can give pi over 2. I can give pi. I can give 3 pi over 2. I can state 2 pi here and then go, nope, because it can't equal it, correct? So my non-permissible values would be x can't equal 0, pi over 2, pi, 3 pi over 2. That's it. If it equaled any of those, my denominators would turn to 0, which would cause my calculator to yell at me. I'd be like, no, not happening. Error. Okay? Now we're going to flip over and we're going to do some more of those ones where we plug in stuff and see what we get. We're going to try and reduce them to things. So we need our formula sheet by us. So remember verifying we went over, and verifying the first step was to plug in what your x was and then not cover over each side, right? Stay on each side, get some answers that match, and call it a day. Left side equals right side. Whereas proving yesterday, what we were doing was we weren't proving that something equaled something. I was asking you to turn most of them into a single trig ratio. So you have to do a whole bunch of work until you got it to cancel. Okay? Today are just a few more. So proving trig identities. So yesterday's what we did was I made you work it into a single trig ratio, right? Like sine, cos, or tan. Today we're going to actually prove. What does proving mean? You can go LS, RS, make your little T table. Whatever's on the left stays on the left. Whatever's on the right stays on the right. Your left is here. Your right's here. I'm doing opposite. So whatever's on there stays there. And you work down the left or the right at whatever time you want until you can get them to look the same. Like sine x equals sine x. Or sine x cos x equals sine x cos x, right? Then LS equals RS. That's what a proof is. Yesterday we weren't doing proofs. We were just doing, here's one side, get it to a single trig ratio. Okay? So to prove a trig ratio is true for all values, making it an identity, we do a left side, right side proof. We cannot cross the equal sign. You're not allowed to, correct? That was one of the key things. Also, if you verify, is verifying a proof? When you put in one value, was that a proof that it worked for everything? No, we showed that even if though it worked for one, we could find a value where it didn't work for another, right? You could show a million examples where it verifies, and it's still not a proof. You just verified for a million that it works, right? So a proof, you can't plug a value in for x, but you can plug in formulas off your formula sheet. So there's no set way to do each problem. That's the biggest problem about proofs. It's not like when you see this, you always do this. There's no such thing as that. Okay? So the more you do, the better you get. But here are suggestions for proving identities. You may use one, all, or none of them. So transform the most complicated side of the equation into the simpler side. So you go to the most complicated side first and try and make it simpler. And sometimes it just matches the other side. Sometimes you get it simpler and then you have to go work to the less complicated side after. Substitute one or more basic trig identities to simplify expressions. So those are the formulas on your formula sheet. And know how you can rearrange them. Like if I see 1 minus sine squared x, I immediately go, hey, I can put in cos squared x. Why? Because I've done this a long time, obviously. But you practice enough, those will start popping out of your head too, right? And remember I told you the single trig ratios, so like sine x is 1 over cos x. I could say sine squared x is 1 over cos squared x. The single trig ratios can turn to degree 2s, yes? But the degree 2s can't go to degree 1. So an example of that was when we had the Pythagorean Theorem. So if I have sine squared plus cos squared equals 1, that's all I can use it as. I can't say sine theta plus cos theta equals 1. I can't like drop that down to take square root of it or anything like that. But these babies, the single ones, I can make be double, degree 2s. Okay? Factor to simplify expressions. If you see factoring, if you see something that's like sine squared x plus sine x minus 1, it screams, hey, I could factor this. It's just got weird signs. Okay, look for factoring. Or GCX. Multiply expressions equal to 1. So for example, 1 plus cos x, 1 plus cos x. Express all trigonometric functions in terms of sine and cosine. As many as you can. If you're stuck, change a tan to a sine over cos. Change a cotan to a cos over sine. Right? We'll run over stuff like that. So let's look at these babies. We're going to prove them. So the first thing we're going to do is we're either going to, I've seen it, either way you can do this. You can go ls equals rs, write the left side in, write the right side in, or they literally just write the left side above, write the right side above, and don't put ls, rs. Like they literally put the equation piece and the equation piece up here. Either one's totally fine. I've seen both, and they're both verified perfectly okay. So I'm going to go ls, rs, write ls here, so cosecant x over secant x, and write cotan x here. Okay? I know which one looks more complicated to me, but maybe it doesn't equal the same to you. But to me, the left side looks more complicated. Okay? They're both singles, so all I can do is look at those top ones. That's all I got. What's cosecant the same as? 1 over sine, yeah. But now I have a fraction. And then I'm going to stack a fraction. Do I ever stack fractions? No, stop yourself and write them out sideways. Okay? If you can stop yourself from doing that, you'll make your life so much easier. Then I'm going to go divided by, what's secant? 1 over cosine. Do I have to work this side down with me if I use the table? Nope. If I put equal signs in between, I would have to go this equals this, this equals this equals this, and work my way down. But if I have a table, I'm showing the left side's working down this way, I'm showing the right side's working down that way. I don't even have to touch the right side yet. What could I do to the left side still? Multiply by the reciprocal. All proper terminology. Very good. 1 over sine x times, then the right side flips, cos x over 1. What do we get there? When we have a fraction times a fraction, we do numerator times numerator, denominator times denominator. The only time you actually do like numerator times denominator and denominator times numerator is when there's an equal sign in between and you're cross multiplying, right? So we're not going to do that in here because we can't go over the equal sign. So it'd be top times top, bottom times bottom. Yeah.
Only max. ls does equal rx because cos x over sine x is equal.
Ah, look at him. So this is what I have to tell you. This right here is the saddest moment of my life. This is the saddest moment of my life when people do this and then go ls equals rs. Because my kid in grade 5, who knows absolutely nothing about trigonometry, if I said to her, Isla, does cos x over sine x, is that the exact same as cotan? She'd be like, I don't know what any of that is, but I can tell you that they don't look the same, right? Right? We should be able to have a toddler come up at the end of your statement and be like, yes, mommy, those look the same, right? So when you go ls equals rs here, we are the saddest humans marking, because that is not true. That left side does not look like that right side, does it? And we can be like, we assume you're geniuses, and you can do that, but we can't assume. We're not allowed to. That's illegal. So I either have to change the right-hand side to cos x over sine x, or change the left-hand side to cotan x, so they actually look the same. Correct? Yeah.
If you like change like cotan to cos over like sine, would you have to like further it back to like cotangent?
Nope. Then they would match.
Okay.
Right? Then my kid could look at it and say, cos over sine, I don't know what any of those are, but they look the same. As long as a toddler could look at it and say, they're the same, you're good. So that's the thing with marking these that makes it a little harder for us, is we actually have to go through and see top down, bottom up, did it actually match? Because I could now go cotan, which is what I'm going to do because I'm a rebel, and these look the same now, right? And I can go ls equals rs, or you could have went cos x over sine x, and then they don't put this, right? That is cos x over sine x, then they match left side equals right side. If you do this, if you turn this into cotan and turn this into cos x over sine x, and then say they match, they don't match again. You just made them unmatch. Don't do that. So at the very end of your proof, this has to look exactly like that. A toddler has to look at it and be like, yes, those are the same. And then left side equals right side. Okay? Make sense? All right. Look at, there's a beautiful try. Try it. Go. Let's use an else.
That one? Tell me more about that. Just like this one? Yeah, that's close. X. Which, I don't know.
Remember, your first step should be to just rewrite the left side on the left side and the right side on the right side. Right? You don't want to work from it into it, because then you're not proving the left side equals the right side. You're proving some other weird transformation of it is equals, right? So your first step is to rewrite the question left side and left side, right side and right side. Okay? Cosecant is what? 1 over sine. Tan? Sine x over cos x. Secant? 1 over cos x. Cos x is cos x over 1. And then you can leave it as, I don't know why I'm rewriting it. You can just leave it. Okay. Now, because these are all multiplied, there's no plus or minus signs in there, is there? If there's plus or minus signs, you can't just go crossy like. No. If there's no plus or minus signs, if they are the same on the top as they are on the bottom, you can cancel, right? Plus or minus signs throw a loop into the problem, which we'll have later, but not right now. Okay. So sine x and cos x and cos x, and then I have 1 over cos x, and then that's just secant. Could you have just left this as 1 over cos x, turn that to 1 over cos x, and say left side equals right side? Yeah, we'd be same boat. Left side equals right side. Okay? Same deal. Okay. We're going to look at this one. Sine x over 1 minus cos squared x equals cosecant x. So I'm going to go left side, right side. First step, rewrite it. Sine x over 1 minus cos squared x. Cosecant x. What can I do? 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 Yeah.
1 minus cos squared x is equal to the little big word that's
Pythagorean Theorem identity. Yes. Agreed. So what's 1 minus cos squared if I rearrange that formula? It's just sine squared, right? Because the 1 is on the left, I'd subtract the cos squared, and I would get sine squared. If you don't believe me, it's sine squared x plus cos squared x equals 1. And then I can go sine squared x equals 1 minus cos squared x. So I can take the sine x and rewrite it. I can take the 1 minus cos squared x, toss it behind my head, and replace it with sine squared x. At this point, I start getting happier. Oh, my goodness. Why do an addiction? Why do I get happier? Because this sine squared x is just sine x times sine x. That's all it is, correct? So this squared can cancel off this one because there's no plus or minus signs in here. If there were plus and minus signs in here, we couldn't do this. There isn't. When the numerator cancels, what's still left? A really large slanted 1. Do you see when these cancel off? They're just slanted ones. So that's 1 over sine x. And I'm going to be a rebel because this one, I didn't do anything to the left, to the right side. But I'm going to be like, I want to. So I'm going to write this as 1 over sine x. And then I have left side equals right side. You could have done absolutely nothing to this side, wrote cosecant x, left side equals right side. Same thing, correct? You're going to do the trig. The trig has a tan squared x plus 1. I think that might be another identity. I don't. Pythagorean, one with a really large P, of course. Identity. I think it might appear somewhere in there. We should look for it. So the tan squared x formula is 1 plus tan squared x. Is tan squared x plus 1 any different?
I don't think so.
Addition, you can do this. Right? You can arrange them in different orders. Subtraction, totally different ballgame. You have to take a sign with it. But addition, you can flip side. Okay? So, we're going to have left side, right side. Please make sure you're rewriting the question. Tan x over tan squared x plus 1, because this is what we're proving. Sine x cos x. Tan x, for me, is sine x over cos x. Divided by, what's tan squared x plus 1 equal to? Secant squared x from our formula sheet. So I'm going to get sine x over cos x. Secant is what? 1 over cos squared x, yeah. Then I'm going to have to flip it. So sine x over cos x times cos x, or cos squared x, sorry, over 1. Then, do I have any plus or minus signs in here? No. So then I can just cancel off things that match in the numerator and the denominator. So this squared cancels off this cos. And now I have sine x, and now I'm just happy as human. Because I see some matchy-matchy happening here, even though it's green and black. And left side equals right side. Flip over. Uh-oh. It looks different. Oh, the cube is nothing. Don't worry about it. So, we don't stress.
Worried about it.
If you are stuck, paying attention, if you're stuck 98% of the time, I figured it out. I have not. That's a made-up number. But anyways, 98% of the time, it's because you are not factoring or taking out a greatest common factor. 98%. It's a made-up number, but it is big because it is real. Whenever people are stuck and they're like, I don't know what to do, Lepp, it's because usually it's a GCF. So is there anywhere in here that possibly could have a GCF? Yeah.
The scary exponent.
The scary exponent. The bottom right denominator. Is that where you're going? Yeah, sure.
Yeah.
Okay, let's write it up. So we're going to go.
That's what I was thinking.
Yeah, that's what you said. I know. Left side, right side. So we have, first step is to rewrite it. Don't go like doing any crap to it. Just rewrite it. So we have cos cubed A over sine A minus sine cubed A. Now what am I saying? Is that this here, both of them have a what in common? They have a sine A in there, don't they? So I can take a sine A out. Can I not? I'm going to let this side roll. I'm going to go to this side because this one looks more complicated to me. So I'm going to go cos cubed A, and then I can take out a sine A. Now watch yourself. When you GCF, or take a greatest common factor out of two terms, you better still have two terms. Greatest common factor just means I'm making it more simple, correct? So if I have two terms and I'm taking a greatest common factor out, I better still have two. So sine A, take out a sine A, is actually a... What's sine A divided by sine A? 1. There's a 1. It doesn't just evaporate. That's where the error happens. Sine A out of sine A is 1, because sine divided by sine is 1. 4 divided by 4 is 1. 8 divided by 8 is 1. Right? Anything take out itself is 1. So I have two terms here. I better still have two terms left in this bracket when I take the GCF out. So sine A divided by sine A is 1. Sine cubed A, take out a sine A, is negative sine squared A. Huh. That baby rings a bell. A bell of the P formula with the really large number. Like what letter? Not number. So you know what I'm saying. Can't even copy you. Pythagorean Theorem. Boom, boom, boom. Sine squared plus cos squared x equals 1. And I want 1 minus sine squared. So I can subtract it over. Ha! Look at it. Isn't that pretty? So you take the 1 minus sine squared. Shunk, toss it behind my head. Rewrite cos cubed A over sine A. And in this bracket, I tossed that out and I replaced it with cos squared A. And then this might be the moment where you start getting a little bit happier. Is there any plus signs or minus signs happening here? Nope. And when there's no plus signs or minus signs, we can cancel off stuff that matches. This is a cos times a cos times a cos. And this is a cos times a cos. So what can I do? You can cancel. Take these two out for 2 of these. And I'm left with cos A over sine A. Which this is cos A. I ran out of room, so I'm going to change this one. But you could have just said cotan after this, right? Try. The try. Remember that big Trig review I gave you? You have to work on it this weekend.
Is it due or going?
It will be due, because I want to be able to do questions on it. So you guys need to go through and know what you know and find out what you don't. And this little review will help you out with that. Because your test is the following week, right? It's on this plus chapter 6. So go through this. This is going to be due. We're going to go through it on Wednesday. But I would take your weekend to do it. That's up to you. If you don't do it by this weekend, you're going to be doing it at nights when you have other homework, right? So this is due on Wednesday.
Why doesn't give away?